Okay, geometry, this is 7-3, triangle similarity. So go ahead and try these and come back and check your work. 1 to 2 or something like that, right? You can give a scale factor, I suppose. So, okay, number 1, your answer is? Kara, what is it?
I got b equals 14 and 2/3.
Good. So it was 44/3, so you had to divide. Number 2, Matthew.
I don't.
Say the correct answer. It is? Not just 10, but? No, not just 10, but you could say plus or minus, couldn't you? Right? Because z squared equal to 100, don't forget there is a negative root. Okay? And then this one, Andrew, number 3. Good. X is 8. And then here again, similar triangles have congruent angles. They have the same shape, so their angles, corresponding angles are congruent, and their sides are proportional, not necessarily congruent. If their sides are congruent, then the similar triangles are also congruent triangles. So give the congruent angles, Jenna.
Angle Q is congruent to angle X, angle R is congruent to angle Y, and angle X.
There you go. And so we are given the similarity statement, so you just read the statement, and that's great. And then the proportions, let's say QR would be proportional to, and is that the order they put it in? Yes. RS is proportional to YZ, right? And then you could say SQ or QS is proportional to, what did they say? RS to, oh, they gave all the 3 individual proportional statements. So the first side named QR to YZ would be proportional to RS, YZ, and proportional to the third side, which is QS and XZ. So you could write them just as 3 equivalent ratios, okay? So today we are proving certain triangles similar by AA, SSS, and SAS. So which of these is different than a congruency proof? The AA one, right? But if you have AA, think about it. If I have triangles and they have 2 angles that are congruent, what's going to happen? Say it louder, Sydney. Right, the third angle must be congruent. All you need to know is that 2 of these angles are congruent, and now you know the third angle must be congruent as well. So that's why we don't have to say AAA. Okay, and then tomorrow you're going to use triangle similarity to solve problems. So there'll be some proofs tomorrow, but today is going to be the easier day. So there's several ways to prove triangles similar. And again, it goes to the fact that similar figures have congruent angles and then proportional corresponding sides, right? So this postulate is the angle-angle similarity postulate or theorem, and we might be using it. We'll also use SSS, SAS, ASA. No, we won't. These were the 5 that we used for congruency, right? For congruency. And so we're not necessarily using those. We will use AA, SSS, and SAS for similarity theorems. Again, if you use any of these, like HL, and you've proved that 2 triangles are congruent, then can you say that they're similar? Yes. Okay. So explain why these triangles are similar, and then write a similarity statement. Go ahead and pause and come back and. Okay, so good. Andrew's saying that we know that this angle here is congruent to this angle. Why are those congruent? Those angles are? They're vertical angles, okay? So anytime 2 lines just intersect, 2 segments intersect, those angles that are across from one another are vertical angles and they're congruent, okay? And then I heard you saying we also know about these right angles, right? We know angle A and angle D are congruent. So we have 2 angles that are congruent in these triangles. So what can we say about angle B and angle E? They also are. But we don't even have to say that because we have this theorem that says if we have 2 angles that are congruent, we have similar triangles. We don't have to go beyond that because, I mean, the reasoning is a third angle would be third angle theorem, really, right? And now give me a similarity statement then. How would you name these? Triangle, give me the first triangle. Is similar to D, E, C. Does he have corresponding vertices in an arrangement that works? Yes. Okay, who has a different way that you named it? You all went alphabetical? That typically is what people will do, is alphabetical. But let's, okay, you didn't do another one, but make another similarity statement. Go ahead. Everybody make one and we're going to hear what you came up with. Okay, so say it, Michael. Similar to. Did you just use the previous statement to do that? Or the picture? Good for you. I mean, it's easy to use the statement that we know is true to make another statement. We could even go just straight backwards, right? CBA, CED, you know, and there are many ways we could write this similarity statement, so long as you have corresponding angles in correct arrangement, okay? We also have the side, side, side similarity. And this is not, now the side, side, side with congruent triangles, each side had to be what? The sides had to be the same, you're saying, the congruent, right? But now this is different. This is the side, side, side similarity theorem, so the sides must be proportional. That's the difference. So look here, we can say that AB is proportional to DE just as AC is to DF. We've got to take and prove two, though, to be true, right? One statement wouldn't prove it for us, okay? So, and then, same is true with this SAS. We had an SAS congruency theorem, and we had to prove those sides were congruent. Now we simply have to prove those sides are proportional, which means that then they're similar, okay? So we're looking at this just in a little different way when we're dealing with similar figures, okay? So go ahead and verify that these triangles are similar and come back and check. Notice there are no given angles. And it all comes down to angles. I mean, you know, by definition, similar figures have congruent angles, but we do now have a theorem that will help us show that these are similar using the sides, right? Good, so you're going to make it a proportion using what you believe to be corresponding sides, right? And see if it's true. So tell me what you have, Hannah.
I have PQ and ST, they're corresponding.
She's thinking PQ and ST are corresponding.
Because from the statement above. And then.
Oh, okay, from the statement above. How beautiful is that? So the way that this is written, she's using that. Okay.
And then so QR and QR and TU.
QR and TU.
And then RP and TUS.
Okay, so did you substitute the values?
Yeah.
And what does that look like?
It looks 3 over 4.5. 3 over 4.5.
That's easy to see. And then let's test the last.
2 over 3.
2 over 3. And so we really only have to check and confirm that this proportion is true because two of these proportions are identical, right? And so is this true? Is it? So how can you check to know that a proportion is true? Cross product. So what's 3 times 3? And what's 4.5 times 2? I mean, there are other ways, but 9 equals 9. So do we have proportion? We do. Okay, and so the statement is actually written, like Jenna said. I was thinking, could it be possible they would write the statement up here in an order that's not corresponding vertices? They could just say triangle PQR and triangle UST or something. And so it may not be that they give it to you so like such a beautiful gift like they just did. And then you have to say, well, is there another way that these might correspond? And check it. Okay, good. So we really were using the side, side, side similarity theorem, right? Okay, and let's go ahead here. Now we have actually an angle measure given, and yet the side lengths are different on these two triangles. So they're definitely not congruent. Are they similar? So if they are similar, what is the theorem that would be true, Sydney? Okay, so we're saying it would have to be side angle side because we're given two sides and the angle between them, right? And so give me the proportions. Do we know that the angles are congruent?
Yes, I think so.
We do. So this part checks out, right? So we're going to just check the proportionality of those sides. So Sydney, how would you arrange it? Okay, could we flip this proportion upside down? And do it the other way? We'd have to flip both, exactly, right? And that's just the reciprocal property of proportions anyway. It's a property of equality. If you have a true proportion, then you can always flip both of them, and it should maintain equality, okay? And so fill in the value, Sydney.
It's 2 and
2 over 1 equals, and we're testing this really. Is that true? Is 29 times 2 58? Right? We could basically blow this up by a factor of 10, right? And it's true, isn't it? So because it is true, this proportion tells us that we have similar triangles. I guess we should write the statement. DEF is similar, which is one little curvy line, right? HJ, okay. Just like they wrote it again. They gave you the correct form, okay? Okay, how about if we use this to find a missing length? So we know that triangle ABE is similar to triangle ACD. So find CD. Okay, tell us what we need to do.
1, 2, 6, a proportion. It should be 9 over 12.
Okay, so you're saying 9 over 12. How'd you get that?
You add 9 over 12.
Okay, so you're saying, you're basically using AB and AC, right? So if we use the letters given, you're doing AB over AC. Are those we can see they're corresponding given the statement, right? And so he says, instead of writing the segment names like that, let's put the values. And we have 9 over 12. And what side are you making this proportional to? EB and DC. So let's check EB and DC. So that's true, right? So he has a proportion set up correctly here. So what values do you have for those?
5 over x.
5 over x. Okay? And so then we use our cross products or something. What did you use? It's not easy to blow 5 up to become a 9. You know, like the old blowing it up kind of way. So 9x equals...
But you can then get 45 multiplied by 5.
I'm just going to... I heard people say cross product. So what is 12 times 5?
It's
60. So when we divide by 9, what does x equal?
6
And so we're going to leave it as a fraction, right? Because what kind of a number is 2/3? It's a fraction, and it's repeating. So what do we call that? It's rational. It's a repeating decimal, and the decimal is 0.6 repeating. And so we know, we can predict it. It's very predictable, so it's rational. Okay? And let's see if we agree with the key. 6 2/3. Good. There you go. Excellent.